Welcome back, chemistry fans. So excited. We are on the new year. We're on a new unit. This is unit 8. This is all about solutions. Specifically today, we're going to talk about a formula called molarity. Let's jump right into it. So let me share with you my screen, and we are going to talk about these solutions. Now, solutions, of course, to you and me are the answers to problems. But in chemistry, it's something a little bit different. It's going to be this formula that ends up being moles divided by volume. Now, before we jump into this, we need to understand that there is this definition, there's this word, this term that we're going to use in conjunction with solutions and molarity. It's called concentration. Now, if you were to focus your efforts into one task, that's what we would normally say, concentrate, and you might be able to come up with the answer. The reality is that usually isn't how it works. You have to practice to get good at this. There's also to concentrate means to bring together. And this is closer to the term that we're going to want to talk about. And what that means is that you are making more stuff in your flavor, in your more stuff in your liquid. You're going to have a base of water and you add more flavors, you add more stuff, you add more content, and it gives it a higher concentration. Well, in this example of how orange juice is made, it's actually a weird process in that they take the juice from the fruit and they then will pasteurize it so it doesn't grow any bacteria. And in that process, it evaporates some of the water off. That concentrates it. So once we've concentrated it, we then have to add a little bit more liquid to the desire of the manufacturer, either A, to make more money, because if you water down your juice, you get, it costs you less and you're selling for the same quantity because water is virtually free. And then sometimes, though, whenever we have frozen, they will just leave it as a concentrated, and you're the one who has to add the juice, the flavors, the water to it. All right, so what this all boils down to is it's a ratio. So this concentration in chemistry is going to be a ratio of how much of the solid particles there are divided by how much of the liquid there is. And so we have this concentration triangle that we'll probably start seeing again whenever we talk about molarity in just a second. So this ratio, to solve this, what we could actually substitute in here is instead of a C, we could have a capital M for the formula that we're going to talk about. And then this becomes the formula over here, moles over liters. But we'll see about that one here whenever we get closer to the actual formula in just a second. All right, so solutions, definition. Solution is technically not an answer to a problem, but it is the combination of two or more materials in a homogeneous solution, in a homogeneous mixture. So once we start combining two materials, usually it's water and some other material, there is an extent to which they will be able to be added together. You can't just add thousands and thousands of pounds of orange juice into your water. Eventually, it can't hold it and it becomes a solid. So there is an extent to how much of it you can actually add to it and still remain as a liquid. And that's what this graph is showing you. We'll get into that one in the second topic. So I need to remind you of some things you already know about in previous coursework, that when we make a mixture, we have the solid and we have the liquid. Well, they have fancy names. The solute is the solid portion of your mixture, and the solvent, well, it is the liquid portion of your mixture. And when you combine them together and they are homogeneous, that makes it into a solution. So that being said, I need you to understand these terms. Concentration means that it has a lot of the solute particles. And if we then dissolve it with only a few, or we add a lot more water, is what you see in this example, that becomes dilution. That's a dilute. And so you have concentrated and you have diluted materials. And you need to understand the difference. The concentrated has more solute, more solid particles in it. It's got a darker color. The diluted has more water. It has fewer of the solid particles inside of it. I want to remind you that homogeneous means it's the same throughout. In that matrix of blue and red dots, you notice they're evenly distributed. But in the heterogeneous, you notice it's not so much. If I take a scoop out of the top, it won't have the same concentration, the same ratio of red and blue as it does at the bottom. So there are some examples of that one. Air is the same no matter where you go. Hopefully your steel is homogeneous. It's a mixture of two different metals. Your rain would be just water and atmospheric particles, pretty much the same concentration. But if we then look at cereal, oh my goodness, that is heterogeneous, because if you take a scoop at the beginning, it's crunchy. And if you take a scoop at the bottom, it's soggy. If you look at oil and vinegar, you have to mix it up, shake it up to make it the same homogeneous throughout. All right, so now we are ready for going back to our formula. So here is the formula for molarity. Molarity is moles divided by liters. And if you look at this formula here, the way it is written inside of this pyramid, it tells you moles is always on top and liters is always on bottom. If what you do, though, however, is you are given in a problem the molarity and you're given the liters, but they want you to solve for the number of moles, what you can do in this magical pyramid here is you can simply cover up the one that you are looking for and do what's left in the pyramid. So it'll be molarity times the liters times the volume will give you the number of moles. Well, what if in the problem you are asked to solve for the number of liters and you are given the molarity and the moles? Well, in this case, we would cover up what we're looking for, and it ends up moles divided by molarity. And that's how we can solve for it. Or we can go back to the original formula, and if we're looking for molarity, we do the number of moles divided by the volume. And so molarity is going to be moles over liters. All right, so let's jump into these practice problems and let's see what we can do with them. So here we go. Here is question number 6. I've got moles and I've got liters. My formula is moles over liters. So that's 3.4 divided by 2.1. Let's plug this into the calculator. A very simple task. You get 1.6. The units on this one are molarity, capital M. You could write moles over liters, but generally speaking, we just convert that into a capital M. All right. For number 6, I've got grams. That's not moles. So I need to convert grams into liters. That means I need to add up the weight of this barium phosphide. Barium is 137. There are 3 of the bariums. The phosphorus is each 31, and that weight comes out to be 473 off the periodic table. So I am using my previous knowledge of the mole map. Grams to moles, you divide. 670 divided by 473 gives me 1.42 moles divided by the 13.4 liters. And what I get is 0.106 capital M.
Sue or Bertha, please come to the main office. Sue or Bertha, please come to the main office.
Okay, we'll be right down there. All right, number 8. Now this one, it's in milligrams. So my first task is to turn it into grams. Well, to do that, you just divide by 1,000. So it's 7.890 grams. Again, I am in grams. I need to be in moles. So I need to divide it by the weight of calcium sulfide. I look on the periodic table, calcium weighs 40, sulfur weighs 32, and that is 72. So I will take 7.89 divided by 72, and I get 1.096, since I got 4 sig figs there. Divided by, that's my number of moles. I'm going to divide it by the number of liters. Well, to turn it into liters, I just divide by 1,000, or just move that decimal point over 3. So I've got 0.1096 divided by 4.9, and I get my answer is 0.02237 molarity, capital M. All right, Last question on this example is number 9. On number 9, what I've got is the molarity is given. But I'm asking for what is the number of grams. So I know molarity is 4.62. What I don't know is the number of grams. I do know that there are 0.75 liters, again, divide by 1,000. So what this will give me is not grams. This is going to give me moles. So 4.62 times 0.75 gives me 3.47 moles. Three sig figs, yep. Now, how do I convert moles to grams? I do the reverse on the mole map. I multiply by the weight of salt. If I look up on the periodic table, salt weighs 58. So that means that my final answer is 200.97 with sig figs. It would be 201 grams. Okay, so this is how we work with molarity. All right, last little bit of formula here is what you will find out in tonight's homework is called the dilution formula. In the dilution formula, you could use this molarity formula twice. Or what we could do is understand that there is a relationship before and after, that because it's in the same container, it has the same amount of stuff. All I've changed is the number of the water particles. So I have the same molarity. I have the same number of moles of solute up here. What I don't have is the volume has changed. So it ends up that the formula is just M1V1, the values before you dilute it, and then M2 is the new molarity, and V2 is the new volume after you've added more water to it. So let's then see what happens to the molarity as you dilute it. If I keep adding 1 milliliter of solution to these cups, what happens is it continues to drop in molarity. Every time I add 1 more milliliter, the amount of moles stayed the same, the stuff, but what changed is the dilution. I continued to make it more and more dilute. Okay, so 2 examples and we'll call it a day. So in this one, I have a molarity of 2 and a volume of 5. It has a new concentration after we're done diluting it of 1. I don't know what my new volume is. So what I'll do is I'll divide both sides by 1. 2 times 5 is 10. 10 divided by 1 is 10 is my new number of liters. So I went from 5 liters to 10 liters. I doubled my amount, and that reduced the molarity in half. All right, let's try one more. So in this one, I've got 10.4 and a molarity of 6.3. It doesn't matter the order, but I've added 3 liters. So 3 liters of water goes into this one. So now it's 13.4. I don't know what my new molarity is. So this one I cannot do in my head. So I will divide both sides by 13.4 into my calculator. 10.4 times 6.3 divided by 13.4, and I get 4.89 as my new molarity. Okay, last variation on this exact same formula is neutralization. Neutralization works the exact same way, except we have to account for the fact that sometimes an acid dissociates, breaks apart into more than its original amount of molarity. In other words, this HCl right here, it has 1 acid particle. This base, NaOH, has 1 base particle. But if I had H2S, or if I had BaOH2, what that means is that I will have 2 hydrogens, I will have 2 hydroxides. So you have to account for the number of hydrogens and the number of hydroxides. And in this case, the molarity would be multiplied by 2 for both of those. So let's jump into a neutralization problem. So in this scenario, it's the exact same math as M1V1 equals M2V2. Instead, though, of it being before and after, now we have acids and we have bases. So we'll keep the acid molarities together, 0.75 and 4.6, and we will now put the base. I'm going to neutralize it with 0.35, but I don't know what the molarity of the base is. So I'm going to multiply these together and divide both sides by 0.35. So I've got 0.75 times 4.6 divided by 0.35, and I get the molarity of the base was 9.85 for it to neutralize, for those two amounts to become equal. Now, if this acid happened to be diatomic and this base happened to be triatomic, well, then what we would have to do is I would have to multiply the base by 3. I'd have to multiply the acid by 2. That's if there is mention of the number of OHs or the number of Hs. If they're not, we just don't worry about that detail. Okay, so I believe that this is everything that we need to cover today for this lesson. Thank you so much for your time. I will talk with you again soon. Bye-bye.